Good afternoon. It's my great pleasure to invite you to this Vignayana Kathegalu and also to welcome our speaker, fellow Indian cosmologist Nissim Kanekar. Nissim and I go a long way back, but before that, let me say he is one of the rising stars, or maybe already risen stars of Indian cosmology. Recently won the Infosys Prize, and then probably a few years back, the Shanti Swarup Bhatnagar, and on and on. Of course, I know him for many years because he started off with his PhD on very exciting work, and everyone seems to be whispering there's a great kid around the block. I was hoping to have some juicy stories because, he's right across the road from Ayuka. Today I looked up his wiki page and realized why. His PhD period exactly coincided with my postdoc period when I was not in Pune. And hence, I think you went off in 2000 for a postdoc to Netherlands, and then a couple of years there, and he was at Socorro at the National Radio Astronomy Observatory with a couple of very, highly regarded fellowships, Jansky Fellowship and Max Planck Fellowship. And then 2009, the boy returned and GMRT celebrated. And he has been at NCRA since 2009, and he's been doing great work on looking for neutral hydrogen and also constraining the fundamental parameters and their variations across cosmology. And so without taking more of your time, let me call upon Nissim to take the stage. Thanks, Nissim.
Thank you. Okay, I'm going to stand over here because I hate standing behind lecterns. I can formally tell you that everything that Tarun said was entirely untrue. So, we go back a long way, and it gives me the right to say that. So I'm going to be telling you about atomic hydrogen and galaxies about 9 or 10 billion years ago. But before I start, I should say that a few things. First of all, I need to acknowledge two people. One is Govind Swarup, the person over here, who basically led the design and the building of the GMRT, which is the telescope very close to my heart, and which I'll be talking about a lot today, and who actually set up our group, which is much more important, I would say, than merely building a telescope. And the second person who is really important for this talk is Aditya Chaudhary, the PhD student who did the bulk of this work. So I'm kind of swanning around the place taking credit for his work, really, which is, So Aditya should be given the bulk of the credit for the results I'll be telling you about. The second thing that I should mention, which the more astute amongst you will have already noticed, is that I tend to speak a little fast. And I tend to remind myself every, the start of every talk to slow down and to, speak at, whatever, 2,000 words a minute rather than 10,000. But I forget after about 5 minutes. So I will rely upon you to, wave an arm, throw a chalk, do something to attract my attention, and then I will slow down. If I go too fast, then I will slow down. That's about all I think I had to say. But the one last thing is that feel free to just, to interrupt whenever you like, and we'll take questions whenever you like, and you don't finish, the slides. Okay, so let me start by saying that I'm going to follow a maxim of Max Delbruck, an advice that he gave to Alfred Hershey's. I will apologize to some of you in advance. I'm going to assume complete ignorance and absolute intelligence on your part. Right? So therefore, I will say a number of things, I think, which many of you will be familiar with, but I will ignore the fact that you're familiar with them. And I will hope to say a few things which I'm not familiar with. Okay, so what's a galaxy? Start with that, right? So galaxy, most of us, the way we think about it is that you'd say it's a collection of stars. And that's a picture of a very pretty galaxy, the NGC 6946, often called the Fireworks Galaxy. It's had about roughly 100 supernovae in the last century. A very spectacular galaxy. It keeps popping, a firework every so often. And you see these beautiful spiral arms going out. And that's, of course, an optical image, a fairly nearby galaxy. Very pretty, similar to the Milky Way. But now when you look at this galaxy in a different tracer, not in the optical, but in the radio, what you see is this. And so this is an image now of the gas, the atomic gas in NGC 6946 on the same scale. So the gas goes out way, way, way beyond the stars. The stars are tiny on the scale of the gas. Although, interestingly, the mass in the stars is much more than the mass in the gas. In this galaxy, it's about 10 times more. In the Milky Way also, it's about roughly 10 times more of mass in stars and mass in gas. But the gas goes out a long way, a heck of a long way. And that makes the gas very interesting in terms of probing the galaxy dynamics. And of course, the gas is a source of the fuel for star formation. But the thing I'd like you to take away from this is that a galaxy is not merely a collection of stars. It's got gas. It's got atomic gas, molecular gas, and ionized gas. I'm going to focus on atomic gas in this talk. And of course, it's got these pesky things like dark matter and dust, which I will not really talk about very much unless somebody is unpleasant enough to ask me questions about them. So how do we, this talk is going to be about galaxy evolution. What do we know about the history of the universe, and how do galaxies form? How do we go from the early universe to today's galaxies that we know and some of us love? So we started off very early, about 400,000 years after the Big Bang, with this image of the sky. And this is the microwave background. This is from the Planck satellite. And the scale over here, the red things are small, slightly higher temperature values. Think of temperature in terms of density. Don't worry about the fact that that's temperature. The blue are slightly underdense regions. So slightly overdense regions are red, slightly underdense regions are blue. And the brightest red regions are about roughly 0.0003 Kelvin. So 3 times 10 to the minus 4 Kelvin, right? Really tiny number. The uniform background is about 2.7 Kelvin. So these are really small perturbations on a very uniform background. The blue regions are minus 300 Kelvin. So minus 0.0003 Kelvin, 300 microkelvin. And so that means that the universe was really homogeneous and isotropic about 400,000 years after the Big Bang. And yet the universe today is full of galaxies and empty regions between galaxies. So how did we get from there to here? Right? That kind of begs the question. And so the way we got from this very early epoch to today is via the process of gravitational clustering. All that happens really is that these small red regions, which are slightly overdense, have a slightly higher gravitational pull for the regions around them, for matter in the regions around them, than the blue regions. And so what happens is that matter basically flows from the regions which are underdense into the regions which are overdense. And of course, what happens as a result is that the regions which are overdense become more overdense, because of which the gravitational pull goes up, because of which more matter flows in, and they become more overdense, and so on and so forth, until finally you wind up with a massive galaxy, which is a super overdense structure. So let's look at what that looks like. So again, over here, the light colored regions are overdense regions. So this is an overdense region, this is an overdense region. The blue regions are underdense regions. And we started off, let's go back a second. We started off at redshift about 20, where you can see things are fairly uniform, visually at least. And what you see is that matter is flowing from these blue regions along these filaments, along these thin stripes, into these overdense regions. And as time goes by, you'll see, if you focus on, say, on this particular region over here, you'll actually see visually matter flowing along over here. And that is really the process of gravitational clustering, which results in the formation of gigantic structures over here. The scale over here is 50 megaparsecs. For scale, the distance between the Milky Way and Andromeda is about 1 megaparsec. So this is like the size of a very, very, very big cluster. I mean, this region over here is about, let's say, 10 megaparsecs, 8 megaparsecs in size. A gigantic cluster of galaxies, right? But this is only gravity. All the physics that has gone in over here is just simple gravity. So basically, it's like saying that I'm going to take a bunch of particles, which are dark matter particles, which don't interact with each other in any way other than gravity, and just ask what happens to these particles when I chuck them into a universe which is expanding, right? And so what happens is that you form these overdense regions, which are dark matter regions. That's not telling you anything about galaxies as yet. Because remember, galaxies have baryons. They have us. So, we're not dark matter. So therefore, how do you get from a picture like this to a real galaxy? To do this, you need to put in baryons somehow. And people have been doing this for a while, and that's where things get fairly messy. Because we understand gravity fairly well. Things are reasonably, the physics is fairly clean, right? We don't really understand the interactions, the complex interactions that go into a galaxy. So let's look at what happens once you put in gas. So this is now an image of gas. The scale is now 20 kiloparsecs, a factor of 1,000 down from what we had in the previous image. But you see the same kind of gas flows coming in over here. The box over here shows the stars in the central region of this galaxy. And you see these small blobs over here, which are much smaller galaxies coming in. The redshift is shown over here. So as redshift decreases, time moves forward. This is about 11.5 billion years ago. And you're slowly going forward. You have these weird mergers happening. So what's happening is that you have stuff coming from the space between galaxies, the intergalactic medium. The gas is flowing into this galaxy, flowing in, probably along these filamentary structures, landing inside this galaxy, forming stars. The stars go boom after some time. They chuck the gas, some of the gas, back into the medium around the galaxy, which we'll call the circumgalactic medium, the CGM. Some of that, of the outflowing gas, holds up the gas that is coming in, and some of it, actually ballistically, rains back down on the galaxy. So you have a whole bunch of complex processes, but you see a nice disk starting to form over here already by about a redshift of 0.7, and you see a fairly pretty spiral galaxy in the optical, if you look at the stars over here. And what you also see is that at late times now, this space is fairly blue, which means that the galaxy has actually cleared out a lot of its gas at late times, while at early times, you would have seen the contrast is much lower between the central region and the outside. And that's the last, medium-sized galaxy coming in to whack into the sky. What's the problem with all of this? The problem is that this is a simulation. Yeah?
So this simulation that you have as opposed to the earlier one?
Yeah.
What if I didn't catch exactly
Okay,
what
so this is actually now where you're putting in real physics. You're putting in the physics of gas flows. You're putting in hydrodynamic flows. You're putting in cooling of gas, because for the gas to fall onto that disk, it has to cool. Yes, in fact, you're doing much more. You're doing far, far worse things, most of which you have no control over. You're even putting in star formation. What you're saying is that once the gas has come into the disk and it's crossed some density, it actually forms a star, which the way you do it is that you simply switch on a button and say, I formed a star. And then you say that, okay, the star lives for so much of time, and then that chucks out gas. And that's chucked by saying that simply some of the mass is lost. So it's a very simplistic route. And the reason for that is that it's very hard. This is a dynamic range problem. It's very hard to actually do a large simulation and go all the way down from the scales of the circumgalactic medium down to a star scale.
And this is at the level of some particular region?
Yes, yeah. So this is a zoomed-in region.
GR is not?
No, so what you do is that you actually start with a simulation like the previous one, and then you take a region over there, you seed it with a galaxy, and then you proceed from there. And you usually do that maybe at redshifts of 20 or 10, yeah. And you match, yeah. So that's the game, basically. But the problem is that, as I said, this is a simulation, right? And I don't want to say too many nasty things about simulations, but I will anyway. Simulations should not be believed. They're pretty, they give you, fairly nice results in the sense of looking nice. But especially in things like this, where you have hydro information and you have very complicated physics, where, for example, star formation is a button literally over here, right? So the processes are not well understood, and you really don't know that's what's going on, right? So what do? What you do is that you actually go out and look. So you need to actually go and observe galaxies to understand galaxy evolution. It's not enough to simply do simulations, although we have, in the modern era, we've got these fantastic computers, right, which can really put to good use by making pretty pictures like this. But the way you actually constrain those simulations is by observations. Or if you like, the way you really learn about the universe is by observations. So let's go back now to this cartoon picture of a galaxy where you have this intergalactic medium outside, which is the region marked 4, and then there's a circumgalactic medium. The boundary between the circumgalactic and intergalactic medium is often not entirely clear, but this, you might say, is some virial region around the galaxy, a few hundred kiloparsecs. Let's say the galaxy is 25, 30 kiloparsecs in size. This is about 10 times bigger than the diameter of the galaxy. And then you have a region around the galaxy, which is like the disk of the galaxy, which contains atomic gas. And then you have the central region of the galaxy, which contains molecular gas and stars. So what really happens in a real galaxy is that the gas flows in from the intergalactic medium. It flows through the circumgalactic medium. The part of the flow through the circumgalactic medium is actually not well understood. There are two possible models for this. I won't go into them, but there are two possible ways in which you could come in. Somehow, the gas has to get from here over here. So the gas basically lands onto the disk. It has to cool in order to stay on the disk. And having cooled, you can form neutral atomic gas. The neutral atomic gas now cools further. The way it cools is via metals in the disk of the galaxy, which basically radiate away energy from the gas. And then the atomic gas cools further and forms molecular gas. The molecular gas cools further, and then it fragments under its own gravity. It basically just collapses out, condenses out, and it collapses out, and forms stars. And then these stars blow up at the end of their lifetimes. They throw metals back in the interstellar medium, which cause further cooling. So therefore, you increase the amount of molecular gas which is formed. You increase the number of stars that have been formed, which cause further star formation, and so on and so forth. It's a runaway process, effectively. What stops the runaway? What stops the runaway is that the stars themselves, in addition to providing the metals which cause the cooling, they also blow gas out. So there may not be any gas left in the disk to actually form stars anymore. And of course, the gas is basically being eaten up. The hydrogen is being eaten up by the process of star formation. And now the metals which you're throwing out into the galaxy, into the circumgalaxy medium, are higher. They're not hydrogen. So they're not a source of fuel anymore. So that's the life cycle of a galaxy. And the galaxy will keep doing this as long as it has gas which can fuel the process of star formation, right? As long as there's gas coming in from the intergalactic medium, raining down onto the disk, cooling, forming atomic hydrogen, which then forms molecular hydrogen and then forms stars, and then goes through this whole loop. Right. How do you observe this? So it turns out that you can observe this basically across the entire electromagnetic spectrum. So the regions over here, the circumgalactic medium, are observed mainly in the X-rays. The gas over there is fairly hot, and so you see these high ionization species of atoms, and you observe them in the X-rays. I won't talk about that almost at all over here. The regions, the stars that we already talked about, so I'm ordering this ordered now in terms of increasing wavelength. So the CGM is observed in X-rays. The central region, the stars, observed in optical and near infrared, just the way that we always do it. You can actually observe the stars even in, or the region around the stars, even up to the mid-infrareds and later. Then when you come to the molecular gas, you typically observe that in the millimeter wave bands with telescopes like ALMA in Chile. And finally, you come down to the atomic hydrogen, and that you observe with the 21 centimeter line in the radio wavelengths, right? So you basically observe galaxies by using a whole slew of astronomical facilities. And so what have we gotten out of all of this, right? So the thing that really changed somewhere, a long time ago during my PhD, so until the late 90s, we didn't have too many galaxies that we knew at very high redshift. It was very hard to find galaxies at high redshifts. And so, in fact, during my PhD, the radio galaxies were the highest redshift galaxies. And people were all very pally with us, because the way of identifying the high redshift galaxies was to find a radio galaxy which had a steep spectrum, because people had found a correlation between these steep spectrum radio galaxies, which are really bright at low frequencies, and their redshift. And the optical folk were very keen on chatting with us, because we could give them these steep spectrum galaxies. Sadly, the optical folk did two nasty things to us in the 90s. One, they built wonderful telescopes. So the HST came online in the early 90s. The Keck telescopes came online in the early 90s. And the VLTs, the very large telescopes, came online in the late 90s. And the second thing which was nasty, which they did, was that they just became smart. And that was unfortunate, because they came up with this beautiful technique, which is called the Lyman break technique, which basically allows you to look at a galaxy. So a galaxy has a spectrum which has a shape. And it turns out that there's a very characteristic signature in the spectrum of a galaxy, which is a sharp break. And the break happens at a wavelength of 912.3 angstroms, which is the wavelength at which you basically ionize neutral hydrogen. So in the spectrum of a galaxy, photons at a wavelength below 912.3 angstroms can't escape, because the hydrogen inside the galaxy basically just stops them. So you see a galaxy, happily along, if you plot it as a function of wavelength, you see it as, if you're plotting it, say, versus frequency going in that direction, you see it kind of rising, and then whoop, it just drops to zero. And the reason it drops to zero is that photons above this frequency or below this wavelength just can't come out of the galaxy, because all the photons at wavelengths shorter than 912.3 angstrom are being used up and ionizing the gas in the galaxy, right? So you have this beautiful break. And Chuck Steidel and crowd in the US in the 90s realized that this break is basically telling you what the redshift of the galaxy is. So in the old days, you had to actually go and take a big optical telescope and take a spectrograph and put a slit on a galaxy and say, oh my gosh, is this galaxy at this redshift? What Steidel and company realized was that you don't have to do this. All you have to do is that you just take a picture of a region of the sky at a wavelength such that the Lyman break, or at two wavelengths, such that the Lyman break is between those two wavelengths for a given redshift. What you see is that you see a dropout. You see an object detected at one wavelength, but not at the other. And of course, you should do that in multiple bands. And that's what they did. And so suddenly, by the late 90s, there were thousands of galaxies known, partly because of the big telescopes, which now gave you, high sensitivity, but partly because it's the Q technique that they came up with, and because of which they stopped talking to us, which is a little unfortunate. But anyway, so they found a whole bunch of these galaxies, which is great fun. And now, as of today, extensions of this technique have given you tens of thousands of galaxies at redshifts above 3. Right? And we have more than thousands of galaxy redshifts above 5. So it's fantastic. We now know a ton more about the universe than we knew 25 years ago, which is nice. And so there's been a bit of a revolution, if you like, in the last 2.5 decades in terms of understanding the stars in galaxies. Remember, all of these observations are of the stars. They're optical and near-infrared observations. They're telling you all about the stars. So that's wonderful. And that's kind of this is kind of a canonical example of a truly, truly wonderful image of the sky, which is called the Hubble Ultra Deep Field, which is a really deep, a ludicrously deep image of the sky, taken the Hubble Space Telescope, huge number of HST, huge amounts of HST time, observing just this one region. It's a tiny region of the sky, because the HST has a small field of view, but it's supremely deep. And this image is basically telling you about galaxies. So all of these objects, most of these objects are galaxies over here. But this doesn't tell you anything, actually. Because it just tells you that, yeah, you've got a fantastic image, right? You got a really pretty image of the sky. But it doesn't tell you a damn thing about where these galaxies really are. What you're seeing is a projection of all these galaxies onto a two-dimensional sky, or a curved sky, if you like, right? How do I know whether this galaxy is very close to us or very far away? I don't. For that, I need to give you information about its distance. And that's hard. The three-dimensional problem is an issue in astronomy. And the way you get around this is, of course, with spectroscopy. To do spectroscopy now of all these galaxies is really difficult. But as I said, you can use these Lyman break techniques to shift galaxies. And what you're basically doing now is this. You can't really see this, unfortunately, because of lights. But yeah, this is an example of the fact that you need dark skies to do astronomy. If you're a dark sky viewer, you could see this image. But so that's where we are today. And that's the start of the universe, about 13.9 billion years ago. And what's basically been done is that this image has been taken, and objects have been shifted now to the time when they were emitting. So, for example, an object, like say this object, has now been placed at its location in look-back time. And so you see there's a whole bunch of galaxies back here. Very few galaxies close to us, a load of galaxies in the middle, about 5.5, 6 billion years ago, and lots of galaxies at redshifts of 3 and above, about 11 or so billion years ago. The reason for this, of course, is the wavelength at which you're doing these observations, and of course the depth of these observations. So you see lots and lots and lots of these galaxies at high redshifts. And what is this? What do you get out of all of this? What you get is this. So this is kind of a picture of the evolution of galaxies, a typical galaxy, from a very high redshift, this is about 12 billion years ago, to about, let's say, 11 or so, 10, and so on down the line. And what you see is that very early galaxies were basically train wrecks. There were massive mergers happening at very early epochs in the universe, and it was relatively late, so we believe, and this is an issue of controversy right now, it's relatively late that you actually form these disky structures. You can already see a disky structure happening over here, but this is kind of halfway back. This is about a redshift of 0.7 or so, about 6 or so billion years ago. But early on, you see these very messy objects. So that's a picture that we have from optical imaging and spectroscopy. Right? So that's a picture that we have from the Hubble Ultra Deep Field. And more observations similar to this have kind of shown us similar pictures. That the early galaxies were small, compact, and then there were lots of mergers that happened at later times, which slowly evolved to produce these big disk galaxies at late times. And this is one of the things that is being challenged today by the JWST. Yeah?
How do you conceive that the other part of this
Oh, so these are super deep images. So you have an estimate of surface brightness that you're missing. And there's no, I mean, it is possible. You can't rule out the possibility that there is an extended disk, but there would have to be a very sharp change. For example, for this object, the sensitivity is high enough that you would see, if there were a continuous change, you would see it. But so there would have to be a really sharp change, which you don't see typically in galaxies. So there could be, for example, clumps like this, much fainter than this. But there's no continuous structure going out, for sure. Right? So this could be the brightest of a bunch of really tiny clumps over here. And that's likely to be the case.
At what point does the symmetry break and handedness come into this?
That's a good question. That's a really good question. Yeah, but by handedness, you mean the rotation? Yeah. So most rotation in galaxies is a function of local tidal effects. There have been claims very recently that there could be large-scale handedness. And if that were the case, it's telling us about the early universe. But most of this stuff over here, if you take a given region, you'll have a galaxy going this way. And that's because of some tidal pull of other galaxies in the region. If you take another region, it's going the other way. There have been claims in the last few years, 3 years or so, where they've taken large regions of the sky and they find evidence for handedness in that region. And the jury is out, I would say. I mean, a couple of groups are getting this kind of signature. And so I would be wary about trusting it. But so at least as of now, we don't see any evidence for handedness beyond local handedness. So that's the picture in terms of the optical. And taking the same thing backwards, we can look back at the Hubble ultra deep field and look at when objects show up. So now you're basically looking back in time. And so because these two chaps are stars which are in the field, and objects are showing up at the point where the light is coming from them to us. And so you see bluish galaxies in the nearby universe. And as you go further and further back, you see they're smaller and smaller. And they're fainter and fainter, of course, but they're also smaller and smaller. And that red chap, which is really, really tiny, comes up right at the end. And it's very hard to spot it on this image. You really zoom in. But you can see that this object, for example, is a big object which is formed a long time ago. We're seeing its light as coming to us from around 8 or so billion years ago. But that is a massive, massive object which must have been formed much, much earlier. And now it's red, which means that it's actually eaten up all its gas. And the stars have basically aged and died. And it's now an old galaxy, although it's so massive. So there are galaxies fairly early on which were massive, which formed stars very rapidly. These are called starburst galaxies, and which became what are called red and dead galaxies about 7-8 billion years ago. So there's a mix of galaxies, but a typical galaxy very early on is small. A typical galaxy at late times is big. That's the picture to take away. And this is one of the things which is being challenged by the JWST right now. And again, the jury is out on that. There is evidence being found of large galaxies at very early redshifts. Tentative evidence, so again, don't jump onto your horses for new cosmology as yet. So what have we gotten from all of this, right? So we've got a whole bunch of spectacular images, of the sky from a bunch of spectacular 10-meter class telescopes in wonderful locations, and from the HST, right? If you have to put one figure down which encompasses all this information, I would argue it's this one. Well, it's not exactly this one, but it's a variant of this one made with a different x-axis. So I've converted this. So this is a figure which shows the star formation activity of the universe as a function of look-back time. This figure is normally plotted as a function of redshift, but look-back time is a more familiar concept, so I just shifted that into look-back time. And what you see is that very early on, 13 or so billion years ago, the star formation activity was very, very low. And then you see this rise in star formation, and it goes up and up and up and up and up, and rises by about a factor of 10. So this is to scale, so it rises by about a factor of a little more than 10 over here. This is about 11 billion years ago. And then there's an era in the universe over here where the star formation activity was fairly flat, right? And so this is the average star formation activity across large numbers of galaxies in the universe. So some galaxies have more star formation, some have less. What you're basically doing is that you're measuring the star formation rate summed over all the galaxies. This is the star formation rate density. It's the sum of the star formation rates in all these galaxies divided by the volume, right, as a function of time. And so this goes on, and then about 8 billion years or so ago, you have this remarkable drop. So this era is often called the era of cosmic noon. It's the epoch at which, if you look at the stars in today's universe, about 50% of today's stars were actually formed in this period. So this is when the universe was most active. It was producing stars like crazy, and was extremely active. And then at some point, 8 or so billion years ago, things stopped. And then you started to see this decline in the star formation activity in the universe. And today, we are actually living in a very quiet, placid, peaceful universe. Very boring, actually. I mean, things were much more happening, so to speak, 8 billion years ago. So we are about a factor of 10 or more down in star formation activity today. We are almost at the point at which things were, let's say, about 12.5 billion years ago. Now, you can kind of, in a hand-waving way, understand why the star formation activity was low in the beginning, right? Because to start with, you need to produce gas. You need to produce galaxies. So the early galaxies were small. There's atomic gas. Now, you need to convert atomic gas into molecular gas, right? You need to cool. The early galaxies don't have too many metals because there hadn't been too many stars beforehand. So therefore, cooling is a much slower process. So to start with, the initial phases of a galaxy's life have very low star formation activity because most of the stuff is in the form of gas. And then you form the first stars. The first stars live a certain amount of time, and then they go boom, and they put metals into the gas. And that causes the star formation in these galaxies to go up. So you expect, in a hand-waving way, this rise. Not the details of exactly how long it will take, but approximately that things should be low in the beginning and then go up. Sounds plausible. We have no understanding of this flattening. So that's one of the big lacunae in our understanding of the evolution of the universe. And then, and we've known this plot up to about here for about 25 years. We've known this to about here for about 15 or so years. We had no idea why this happens. Right? So there's this decline by a factor of about 10 over the last 8 to 10 billion years. And we have no idea about this. So these are two big open questions in galaxy formation and evolution for the last, say, 20 or so years ago in terms of the evolution of galaxies. And clearly, I mean, you can kind of say that, again, in a somewhat hand-waving way, there must be a feedback process. What's probably happening is that, as I said in the beginning, that stars are forming, they chuck metals out. Yeah, okay, you keep forming more and more stars. At some point, there are so many stars and so much star formation is happening that probably the stars will start to have an effect on the gas. And we'll start to drive the gas out, probably. And that might actually cause kind of a break, if you like, on the star formation activity of an individual galaxy. Why that would happen across a large era in the universe is a different question. An interesting question, I would say. So for about 3 or so billion years, the universe has a fairly constant star formation activity. The star formation rate density across the universe is fairly flat. It's fairly constant. And then you have this decline, again, fairly constant across the universe. Right? And so why is this? So the obvious thing to do, if you want to understand star formation in the universe, what you should look at is the fuel for star formation, the gas. Right? And that's the thing that we would love to do, and that's been hard. So the pesky optical folk have been having a ball of a time for the last 25 years because of the nice telescopes, and we are playing catch up, so to speak. So that's the game, basically. So what we wanted to do, what we would like to do, is to look at the gas in these galaxies. As I told you in the beginning, the way you look at the gas, the atomic gas, which is the primary fuel for star formation, remember the molecular gas is the proximate fuel for star formation. It's what actually is converted into stars. But the primary fuel is the atomic gas. That's the gas which is coming into the galaxy and going into the molecules. So you'd like to look at the primary fuel. So the atomic gas is the primary fuel. As I told you a long time ago, you need to look at the 21 centimeter line. This actually has a story by itself. But the beauty about this signal, which is a spectral line, it comes from a spectral transition within atomic hydrogen. And it was actually identified by a PhD student in the middle of World War II. So it was, while the Germans were actually occupying Holland, the Netherlands, if you like, although this was in Holland, Jan Oort, who was this absolutely crazy Dutch astronomer, and whose ambition in life was to map the Milky Way. And he spent much of his career trying to map the Milky Way in the optical. So he had been trying to look at the kinematics of the Milky Way. And the problem he ran into was that, as you may have noticed when you look at the sun when it's setting, optical light is affected by dust obscuration. So it's very hard to see through dust clouds in galaxies. So you can't look at certain regions of a galaxy in the optical, of our galaxy in the optical, just because they're obscured by the dust along the sideline, right? So Oort was basically interested in finding a tracer that would let him map the Milky Way in a tracer which was not affected by dust. And in the late 30s, Gert Reber who was the first official radio astronomer, in the sense that he was the first person to publish papers, the first person to publish radio papers in an astronomy journal. So Karl Jansky was the first real radio astronomer, but he published in the proceedings of the IRE, not in the Astrophysical Journal. Reber, for about a period of 10 years, was probably the only official radio astronomer in the world. During the whole, from about 1936 till about 1945, he was the only radio astronomer in the world. He was the only person publishing. And so in 1942 or so, Oort came across a paper of Reber's, which had been published in 1940, and he used to run a colloquium in Leiden. And he said, oh my gosh, there's radio, and so can you identify a spectral line in the radio? So Gert Reber had simply observed a bunch of these galaxies, a bunch of objects, the sun, the galactic center, in the radio. But Oort was smart, and so he realized that if you could find a spectral line in the radio waves would not be obscured by dust, and so you could map the galaxy. So he passed on this problem in this colloquium to a bunch of people. And Hendrik Casimir, of the Casimir effect, took on the problem. He was a staff member over there. And Hendrik van der Hulst, who was a PhD student at Utrecht, he took on the problem as well. And the good news was that Casimir got it wrong. So Casimir said you can't do it, and van der Hulst said you can do it. So van der Hulst actually predicted that there is this 21 centimeter line at a frequency of 1420.40575 megahertz that could be observed if you could build a telescope that can observe this frequency. Which of course, it kind of existed in the sense that Reber had 400 megahertz telescopes, but now you need to do spectroscopy. You need to measure the sky as a function of frequency. And this was challenging. The good news was that, well, the bad news was that there was a war going on. The good news was that there was a war going on because of the war, there were spectacular advances in radar. So both the British and the Germans were building radar facilities. In fact, you could argue that the British won the Battle of Britain because of radar. That's the primary thing, not the Spitfires and the Hurricanes. So they were both building radar. And they were installing radar both in terms of equipment on the ground and on ships. And the Germans were a little more advanced. The British were they were doing low frequency radar. The Germans were doing high frequency radar and building dishes. And so after the war, these dishes were basically sitting along the Dutch coast and the French coast. So Oort, who was also, besides being very smart, he was also very grabby. He went and grabbed a dish and said, I'm going to look for a 21 centimeter line with this German dish, and started off. Van der Hulst came to the US and gave a couple of lectures at Harvard. And because of his lectures, people at Harvard started working on this problem as well. And the thing that makes me very happy with radio astronomy, which I'm happy to be a radio astronomer, one of the reasons is this, is that what happened as we were going along was that Muller, who was the engineer working with Oort, who was building the receivers, the two of them were working on this problem, and they had a bad fire, in the Netherlands. And the part of their equipment basically burned down. And so they were delayed by about 4 or 5 months. During this time, Purcell and Doc Ewen and Purcell basically detected the 21 centimeter signal, right? Now this is a spectacular detection, right? The first spectral line in a completely new field. If this were to happen today, there would be people, first giving press releases left and right probably, but also then charging off to Nature or Science and saying, hey, me first, and so on, right? These guys didn't do that. What they did was that they sent Oort a telegram and said, we found the line, and asked, have you found it as well? And Oort said, no, we've been delayed. What they did was that they waited. They actually said, we'll wait. They let Oort and Muller repair their instruments. They let them do the observations. They let them get the result, which they'd already gotten. And then they published back-to-back papers in Nature. Now, that is good science for me. Right? And what actually happened in parallel was that Chris Christensen and company also did the same thing in Australia, and that paper also came out in the same issue of Nature. So there was this collaborative attitude. It may have been, again, part of the war ethos, but it was healthy. I think that's how science should be done. But the point remains that even today, the 21 centimeter signal from a galaxy is accepted as being proportional to the atomic gas mass. This is not entirely true, But it is approximately true. It's approximately true in the limit where the signal is optically thin. There could be errors at the level of about 20 to 30% in the mass. But that's a pretty impressive thing. If you think about measuring the mass of an astronomical object to 20%, that is something. It's quite impressive. And so that was the game in the 40s. And then in the 50s, people started detecting signals. So in the mid 50s, the signals were detected from the LMC and SMC, our nearest neighbors. Later from the Magellanic, from Andromeda. And then various people started doing lots of studies in the Milky Way and nearby galaxies. But the problem with this damn line is that it's a beautiful line. It's an absolutely wonderful line, but it's a pain. It's a pain because it's a hyperfine transition. Hyperfine transitions are really weak lines, right? And so they've got really low probabilities of emission. Technically the Einstein A coefficient for spontaneous emission is tiny. It's 10 raised to 23 times smaller than an optical transition. So this line is wonderful and painful. And that makes it hard to detect in a distant object. The further away the object is, the fainter the emission is. And because this line is so intrinsically weak, it's very, very hard to detect these lines at high redshift. For a comparison, today, and this is an embarrassing comparison, the highest redshift at which we have a spectrum for an optical galaxy or an optical spectrum is about 11.2, maybe 11.4. People argue about this, but in that neck of the woods, there are a whole bunch of galaxies with redshifts of 8 and 9, right? In the radio, we still are working in decimals. So the highest redshift is 0.376. And we have a bunch of galaxies that are redshift of 0.25. So if you can push to 0.4, that's an achievement today, right? So, and that's just because this line is so darn weak. So what do? There's two ways of handling this. The first way is to build really big dishes. So that's a picture of the GMRT. And the GMRT's primary science goal when it was being designed in the early 80s was actually literally to look for 21 centimeter emission from really distant galaxies, from a redshift of 3. And the reason for that is funny and a little unfortunate. At that point of time, the two competing models of the universe were hot dark matter and cold dark matter. So people had kind of agreed by about the 70s that dark matter must exist in the universe. Non-baryonic dark matter must exist. And the question was, what is this dark matter? The preferred model at that point, so the two models were either a relativistic particle, which could be a neutrino, for example, which was a known particle, or a non-relativistic particle, which was a theoretical particle. So of course people liked the idea of a particle which existed being the dark matter, because then you don't have to add a new particle to your standard model of particle physics. And also it seemed as though the initial simulations suggested that the patterns of structure that you saw in the universe match the patterns that you got from the hot dark matter simulations. So why does all this matter? This matters because the way in which structure forms in hot dark matter is very different to the way in which structure forms in cold dark matter. In hot dark matter, the neutrinos are relativistic. So remember I started off by saying that, okay, I have this region which is overdense, higher gravitational pull, more stuff flows in, right? But now think of a neutrino sitting over here. The neutrino actually is moving really fast. So on a time scale on which this structure is flowing in, stuff is flowing in, the neutrino moves some distance away. So what it does is that it actually smooths out overdense regions on some scale. It basically it wipes out structure below some size. And the result of this is that in a hot dark matter kind of cosmology, you produce structure first in the biggest objects, and then you produce smaller structure by breaking up those objects. So you produce structure in a top-down kind of way. On the other hand, in the cold dark matter cosmology, this problem of the particle traveling long distances is not there. The particle doesn't go very far. So therefore you don't smooth out structure. So you form the smallest structures first, and they merge and form bigger structures. So you form structures in a bottom-up kind of a way. And in the early 80s, people were thinking that hot dark matter was the most plausible model. And so how do you test this out? The way you test this out was that you go and look for the clean prediction, which was that in the hot dark matter model, you expected to have these gigantic supermassive galaxies at very early times, at a redshift of 3 or so. But in the cold dark matter, you didn't expect to see them. So what Govind and company did was that they said, okay, fine, we need a big telescope which can observe at a redshift of 3 about 11 billion years ago. And so he went off and tried to build one, which was the GMRT. And he got the funding for it with this as the primary science goal. Fortunately, he also planned a whole bunch of other things that, that you could do, which is why, the GMRT has been doing great work for the last 25 years. Because unfortunately, about 8 years after the GMRT was proposed, in 1992, the Cosmic Background Explorer went up, the COBE satellite went up, and that basically killed hot dark matter. It turned out that the Cosmic Background Explorer could actually measure the amplitude of the perturbations in the microwave background, and it could tell you directly, and we can talk about this more detail later, HDM would not work. The earliest galaxies you could form in hot dark matter were redshifts of 1, 8 billion years ago, and even then, people knew there were galaxies at redshifts of 3, 3.5. So hot dark matter would not work. GMRT's primary science goal was basically not possible anymore. I mean, it was just, the thing had been ruled out already. And so the GMRT continued doing stuff. But it remains the biggest telescope in the world, the biggest interferometer in the world at these frequencies, right? So that's wonderful. So that's what you really want to do. You want a big telescope, and you want to look for these signals. But how do you look for these signals? I'm back to square one. I built a big telescope, which is now not sensitive enough because the 21 centimeter line is so weak. So can you get around this problem? And remember, what we really want is not to measure the masses of one galaxy. What you want is look at the population and to work out what is a typical galaxy at these redshifts. So the way to get around this is to use lies, damned lies, and statistics. So that's what the idea is, that although the signal is really weak, what you can do is that, suppose I can observe a large number of galaxies simultaneously, and I know the redshifts and positions of those galaxies. I can now add the signals of those galaxies together, and those signals will add up. So what's been done over here is that this is a slice where each red circle is a galaxy, and each slice over here is actually in frequency. So this is where the signal of this galaxy is. And so you take a small box around that galaxy, place it on top of the other boxes. So you take, for each galaxy, you take a box and place them on top of each other and simply add them up. All of this stuff is noise over here. You're not detecting anything, and you don't detect anything at all over here. So you just keep adding these signals. What's happening now is that the center of the image over here, which is the averaged image, now has the emission of all these galaxies coherently added up. They're all in the same location, and they've been aligned in velocity in redshift. So the signals are right there. And the regions around, the noise is basically cancelling out. Because for any galaxy, there could be positive values here or negative values here. So it'll just fluctuate up and down. So if I can just add the signals of a large number of galaxies, I can get a signal. And that's what the simulation is showing. So this is now doing, you'll see that this goes on for about 400 galaxies, and you see this beautiful signal coming out over here. So that's the game, basically. If you can, and so the big if, of course, is that this only works if you have enough galaxies. And you need a lot of galaxies. 400 doesn't quite cut it. Right? So that's the issue. You need to have a lot of galaxies within a small region of the sky such that your radio telescope can look at all of them simultaneously. If they're spread out over the sky, this won't work. So they all need to be in a small region. So you need to have a good friend in the optical community who will actually go and measure the positions and the redshifts of these galaxies such that you know exactly in which slice the signals come. Now you can go and do a really deep observation with a radio telescope and use the positions and redshifts of these galaxies, combine the information, and boom, you've got a signal, if it all works out. And so that's what we've been trying to do over the last decade or so. And we tried this about 6-7 years ago, and basically did it with the old GMRT. This is with people from RRI, Dwarkanath and Shiv Sethi, and sadly we didn't see anything. So we had just 800 galaxies because that's all, with the old correlator, that's all we could handle. So and that's another message, I guess, in astronomy, that technology really matters in astronomy. It's one field where a small jump in technology can really make a massive impact. So with the GMRT earlier, we covered only 30 megahertz, 33 megahertz in one shot, which meant that when you do a single observation, you're only covering a small frequency range, which means you're covering a small redshift range. You're covering only a small number of galaxies, which is about 900, 850 or so galaxies in this case, right? And this was, it was 250 galaxies in 4 separate observations. Yeah?
In this wave stacking, are they all at the same redshift?
They're not at exactly the same redshift, but they're at nearby redshifts.
Okay, because, yeah.
Yeah, they have to be at nearby redshifts.
Nearby redshifts,
Yeah.
because you're sort of assuming that their 21 centimeter line is going to be the same. And so
No,
within
not
the
really.
error of...
Not really. So that's the point. So each of these slices over here is actually a different frequency. So as long as I cover a big enough frequency range, I will cover a wide range of redshift. So the line is redshifted down from the rest frequency, which is 1420 megahertz, 1420.40575, down by 1 plus z. So the observed frequency, so for example, suppose I have a galaxy at a redshift of 1.
Yeah.
Then you get 1420.4 divided by 1 plus z, which is 2. So it becomes about 710 megahertz.
Right, but when you stack them
Yeah.
together,
Yeah.
you have to then compensate for that, right?
Right.
Because otherwise you're going to get...
Yeah, all I need to do is that I need to be able to take to produce a spectral cube. So this thing over here is actually, ouch. This thing is the first plane of the cube. It's one frequency. And so all of these objects have the same approximate redshift, all these galaxies. The next slice has all the galaxies, which are different galaxies now, which have slightly different redshifts. The next slice have slightly different redshifts, and so on. So if I take any region of the sky, there will always be some galaxies with roughly the same redshift. So all of those will be in one plane. But the next plane over here, if you look at slice 3, they are not the same galaxies. Yeah, so you see that these now are at completely different locations. And in fact, this is the point, that in the old GMRT, because we had a narrow bandwidth, we could only cover a small frequency range, which meant we could only cover a small number of galaxies. If I can cover a large frequency range, I cover a much larger number of galaxies.
Then you basically use the redshift
To separate. Exactly, yeah, yeah. So in fact, technically what we are doing is that we are shifting to the rest frame of each galaxy. So that's the game. And so that's what we've been trying to do. The reason this was possible is that the GMRT was upgraded about 4 years ago. We finished the upgrade 4 years ago. And we moved from, we had the same number of antennas, but we completely changed the electronics. So now we have a much bigger bandwidth, 400 megahertz. And this meant that we could cover much larger redshift ranges in one shot. So what we've been doing is that with 3 PhD students, we've been covering this time range in look-back period, which corresponds to a redshift range of about 0.2 to about 0.4. This time range, which is, of course, as you can see, the interesting time range, because it covers both the flat part of this star formation activity and the declining part. And then right now we are pushing to even earlier look-back times, which is this range over here from 10 to about 11 billion years, right in the peak, if you like, of star formation activity in the universe. And so these are 3 separate projects, and I'm going to focus only on this one, because this one is really, it's kind of, got the science that I talked about so far. So that's cutting to the chase, that's the answer. So that's the signal that we got. This is from stacking 11,000 galaxies, right? So this is akin to the signal that you saw a little while ago from the simulation. That was 400 galaxies. This is about 11,000 galaxies. This is about a 7 sigma result, so high significance. The original signal was about 4.5 sigma, and now we're at about 7. In fact, we've got more data now which pushes it even further. But this is basically the first measurement of the atomic gas mass of galaxies in this epoch of cosmic noon. So this is about 8 billion years ago. The average redshift for these galaxies is about 1, which is about 8 billion years ago, right? Now this is cute. It's all very nice. You can pat yourself in the back. But this is not telling you very much. It's telling you a little bit. Yeah? Yeah, that's the beam over here. Yes. Yeah. 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 So in fact, well, so that's an interesting thing. It turns out that we had to choose a beam size. So the native beam of the GMRT is actually finer than this. But since we want to measure the mass, we want to make sure that the beam is bigger than the size of the galaxies. So therefore, we kept increasing the beam size by throwing away data on the long baselines until we got the total mass. So this is actually one of the open questions now which has come up. This beam size is 90 kiloparsecs, which means that these galaxies are about 50-55 kiloparsecs in size in atomic hydrogen. So these are humongous objects at that redshift, which is not very easy to account for in standard cosmology. So that's a curiosity. There are lots of curiosities that have come up, but that's one of them. That's a good catch. But this beam over here is about 90 kiloparsecs in size. And so this size that you're seeing over here is basically the beam. But we have evidence that these objects are more than about 55. At 55 kiloparsec resolution, and where you see the thing is slightly resolved. Yeah. So this is the first measurement, all very nice, but that's a 7 sigma result, right? This is over a redshift range of 0.7 to 1.5, roughly a look-back time of about 7, as I showed you over here, about 7.5 billion years to about a little less than, about 9.5 billion years. So now what I can do is that rather than taking all the galaxies and averaging them together and giving you a single image like this over here, I can break up the galaxies. I can break up the galaxies into the low redshift part, which is in this part of time or redshift space, and this part, the flat part of the space and the declining part. And I can ask the question, what is the average H1 mass of these galaxies, right, of the two groups? And what you see is this. This is in the same scale. So that's 8 billion years ago, and that's 9. The gas mass in these galaxies is about 4 times higher than the gas mass of these galaxies. And I should mention that these galaxies have been chosen so that they have exactly the same stellar mass. So what's happened is that, so this can be directly compared in terms of stellar mass. They have exactly the same stellar mass. We've chosen weighting such that the stellar masses are the same, right? So this is now an average of about 7,500 galaxies. This is an average of about 3,500 galaxies. Way, way, way brighter. So what this is telling you is that there's this remarkably sharp drop in the atomic gas mass of galaxies just after cosmic noon. They just don't have enough gas left anymore. Why that is a good question. We can talk about that separately if you like. But basically, there's just not enough gas to maintain the star formation activity. And that is the reason that you see this decline in the star formation rate. Basically, what's happened, and this is an interesting and somewhat non-trivial issue. If you look at the gas mass over here, right, I can compare that gas mass to the stellar mass. I told you that in the Milky Way and NGC 6946, today, the stellar mass, the mass in stars, is about 10 times more than the mass in gas. If you look at the mass in the gas in these galaxies, it's actually more than the mass in stars. There's a heck of a lot more gas in the early galaxies than there is in galaxies today. So there's the stellar mass, of course, is lower because stars are being formed as time goes by, but there's more gas than there is stars. But yet, despite the fact that there's more gas than stars, the star formation rate, the star formation activity in these galaxies is so high that the gas is being eaten up much faster than the gas can be accreted onto the galaxy from the circumgalactic medium. So you're basically not replenishing the fuel reservoir of the galaxies because the star formation rate is so fast. And that is what we think is going on over here. So that's where we are today with this stuff. Of course, there's a whole bunch of other things that we are doing with it. The moment now you get to this kind of high significance, you can play all kinds of games. You can break up the data now in terms of redshift, in terms of stellar mass. You can get the dependence of the mass of the galaxy on the stellar mass. You can do all kinds of stuff. You can get the dependence of the mass of the galaxy on its environment, lots of things. But this is, I think, the answer to the big question that we asked in the beginning. Why is there a decline in the star formation activity of the universe at about, let's say, 8 billion years ago? And we think it's because the atomic hydrogen in the galaxy is basically just being eaten up. There's not enough gas coming in to keep the star formation going. So to summarize then, I hope I've convinced you that if you want to understand galaxy evolution, you need to understand both the stars and the gas. And to look at the stars and understand the stars, you need to do optical and near-infrared studies. For the atomic gas, it is the only thing that you have is 21 centimeter, the radio line. The big question that I've talked about today is why does star formation activity in the universe drop in the last 8 billion years? And the approach that we've taken to do this is to try to measure the 21 centimeter signal from these galaxies to measure the atomic gas content. And the problem, as I said, is that the signal is really weak and very hard to detect. And the way that we've been doing this is to use stacking, which combines the signals of many galaxies and gives you a statistical result. It gives you the average H1 mass of the population of galaxies, and it gives you the average gas properties of these galaxies. But that's what we want, really. And the GMRT is a wonderful instrument, upgraded GMRT for 21 centimeter stacking, because it's got this wonderful wide bandwidth correlator and wide bandwidth receivers, both of which have come up in the upgrade. So with the GMRT stacking, we've got the first detection of the signal at cosmic noon, and we found direct evidence that the gas mass in galaxies drops steeply between 9 and 8 billion years ago. And there's no other property that we know of these galaxies that changes so steeply or anywhere near so steeply in that redshift range, in fact, an A redshift range. There's a very sharp change in the gas properties of these galaxies. And there's basically just not enough gas to maintain star formation in the biggest galaxies. And that's another subtlety over here. It's the biggest galaxies which are showing this. It's the biggest galaxies where the gas is being eaten up really fast. The smaller galaxies don't matter. The biggest galaxies are the ones which dominate the star formation activity at the early redshifts. And it's those galaxies where the gas is being depleted, being consumed on timescales of about 0.5 or so gigayears, 0.5, 0.6 gigayears, less than a billion years, which is much faster than the consumption rate today. And that's just because of the very, very high star formation rate in these galaxies. So what we're doing now is that we're doing a detailed characterization of the gas properties of these galaxies, and we're pushing, as I said, to even earlier galaxies. The hope is that we'll be able to understand why did this flattening happen in the star formation activity between about 11.5 and about 9 billion years or so ago. And the next step, we hope, is to expand the GMRT and to actually build to add more dishes. We have 30 dishes right now, double the number of dishes, go to about 60 dishes, and also put in what are called focal plane arrays. Right now we have receivers which can just look at one region of the sky, but you can actually build these multi-pixel feeds, or focal plane arrays as they are called, which can allow you to observe a much, much larger region of the sky. So that's part of the plan to expand the GMRT, and the game there would be to actually detect the 21 centimeter signals of the individual galaxies, and finally bring the original science goal of the GMRT to fruition. Thank you.
Thanks, Nissim, for a wonderful talk. Questions? Yeah.
So I have two queries. One is how it relates to the AGN feedback in these systems. And another one is that whether these galaxies are living in a cluster medium or outside, whether that has been checked.
Yeah, so both are excellent questions. AGN feedback actually is something that we are considering as, so there are, I guess the real question for me is, why is this happening, right? So there are a few possibilities. One possibility that we considered is AGN feedback. So for example, bigger galaxies could have an active galactic nucleus inside the galaxy, and that active galactic nucleus, the AGN, a supermassive black hole, which is accreting matter, can drive outflows of gas and can kick gas out of the galaxy. And that could actually quench star formation. So the first thing is that we actually excluded all galaxies which have known AGNs in them. By that I mean that we have very deep radio images. So any object detected in the radio continuum has been thrown out. So therefore there's no evidence for an AGN in any of these galaxies. So if there is an AGN, it has to be like an obscured AGN or an AGN which is not active in the radio. Right? So that's one. We can't rule that out. So that's a possibility. It could also be an earlier AGN which is not active right now. But again, radio, you should see it, you should still see it. But yeah, maybe you can hide it by saying the radio emission is too faint. That's a possibility. The possibility which I incline towards right now, if I had to pick between these two, is that there's a transition in the mode of accretion in these galaxies. It turns out that, I mentioned this right at the beginning, that the way gas flows from the circumgalactic medium or the intergalactic medium onto a galaxy depends on, there's a debate about how this flow happens. And there are two standard models for this. So one is called, in one, the gas flows in and then is heated up to the virial temperature of the halo, right? So it becomes really hot. Now, in order for it to fall out of the galaxy, it has to cool. The cooling times are very long in this because the virial temperature of the halo is quite large, right? So when the gas comes in radially, spherically if you like, then it heats up to this high temperature, more than 10 to the 5 Kelvin, and then it has to spend a lot of time cooling, which means that the accretion time scale becomes very long. So that's called the hot mode of accretion, and that's, if you like, the classic mode of accretion onto galaxies. The other mode is different from this because the gas doesn't actually come in spherically. It comes in along these streams. Now, when gas flows along a stream, it doesn't get heated up. It doesn't virialize. So it actually flows along the stream from the neighboring filament and falls directly onto the disk. Because of which, since it's not heated up, there is no cooling time scale, or not much of a cooling time scale. Because of which, you can actually accrete much faster. So that's called the cold mode of accretion. Now, we think that in the early universe, in low mass, where the galaxies have relatively low masses, the accretion is dominated by the cold mode. But what happens is that as your mass gets bigger and bigger, what happens is that you make a transition at some point into the hot mode. So what could be happening, and we don't know the answer for sure as yet, what could be happening is that maybe the most massive galaxies at this redshift are doing a transition into the hot mode. If that happens, the time scale will suddenly change. And now you will suddenly take much more time for the gas to accrete on, because of which you won't replenish the supply. So if you like, these are two different ways of getting the same answer. In one way, you throw out the gas. In the other way, you stop the gas from coming in. And we don't know the answer is yet. So the ways to address this would be to actually go and look at these galaxies and find out if they have obscured AGN in them. If they do, then that is a possibility. As of now, there's no evidence for AGNs in these, at least in the ones that we've stacked so far. So that's clear. I mean, we have no evidence whatsoever for an AGN in them. And we've thrown away the ones which have AGNs. Yeah.
Optical also you have?
Oh yeah, so we basically have optical images. We don't have outstanding optical images. We have good optical images, but we don't have HST imaging, for example, for these fields. What we're doing now, and that's what Balpreet is doing for a PhD, we're doing the same stacking exercise in the Cosmos field, which has great optical images, which has great HST imaging. So there we will be able to do this distinguishing even better than in these fields. These fields are the deep 2 fields. They turn out to have really good spectroscopy, but not that good, almost no HST imaging, which is what we would really like for this. So we will answer this question over the next year or two with observations of Cosmos. Your second question was about clusters. And that's a really interesting question. We have tentative evidence right now at about 2.5 sigma that the mass in clustered galaxies is higher than the mass in field galaxies, which is exactly the opposite of what we see in the local universe. There's more gas in those galaxies than in clustered galaxies than in the field. But it's 2.5 sigma, so you can watch this space. We have about twice the amount of time that we observe now in the same fields. We should get an answer on this in the next year or so.
Yeah. So I have a couple of questions. The first thing is about the stacking methodology. So, I mean, if you, let's say, fix on redshift of 1, and you, in a certain patch of the universe, you start stacking in the close neighborhood. That's what you answered, Sumati. Yeah. And you get a certain value of gas mass and so on and so forth. You take a completely separate, hopefully uncorrelated patch of the universe. Yeah. And again, repeat this thing for the redshift 1 candidates. What is the match that you get? I mean, what is the statistical variance on your method?
That's a very good question. So this is basically called cosmic variance in astronomy. So the thing I didn't mention was that we had 11,000 galaxies. These 11,000 galaxies were chosen to come from 7 different pointings. So we consciously at the start, so it turns out that if you want to overcome this issue, so what you need to do in astronomy is that you need to get your average measured over a large region of the sky. So what we did was that we observed 7 separate pointings so that the volume that we get is very, very large. And now, of course, we can compare the results for each of these 7 pointings. 3 of them, so 3 of them are very close to each other. So 3 of them are close, and then there's 2, and then there's 2. And so these three pointings, these 3 groups of pointings are very far apart in the sky. The averages all match.
Individually?
So, individually.
Okay.
Yeah. And that was the reason we did this. We did this so that we could actually check for this effect. And we find no great evidence once we average over these largest regions, and then we have separately 3 regions. So we overcome cosmic variance by doing exactly what you're saying. We take multiple regions of the sky.
Right. So just a kind of follow-up question. So in these candidate things, like for instance, 8 billion years ago versus 9 billion years ago, where you see this change in slope, is there any signature in the optical? I know that you looked at it in a very sparse way about stars, about light in any other band, which has started appearing in a compensatory way in some sense.
No, nothing. Nothing at all. In fact, that is at some level the point, that we see no change in the properties. In fact, not just in this field, in any field. In any of the properties of individual objects across this redshift range. The only thing that we see changes is the star formation activity of the universe, which is an average, an average of the star formation rate divided by density. That's all that we see changing, and that's a slow. Even that is a somewhat slow change. I mean, the change, from here to here is not very large, but this change is fairly spectacular. So there's no property changes anywhere near to this.
Any more questions?
So when you look back at time, then you can only see the signatures of atomic hydrogen in different galaxies. But from that signature, how can you infer the star formation rates at different galaxies?
So we are not measuring the star formation rate from atomic hydrogen.
No, in the another plot.
This one over here?
Here? Yeah.
Okay. No, so the way the star formation rates are being gotten by other measurements. What you're doing is that you're getting the star formation by a number of measurements actually, which is why we are so confident about this curve. You can measure the star formation rate from the ultraviolet light of these galaxies by just looking at the number of bright young stars being formed. You can measure it from the radio continuum, because the big stars go supernovae and they produce radio emission. And that, it turns out, is correlated to the number of big stars. You can measure this from the far infrared radiation of these galaxies, because again, the big stars heat up the dust around them, and the dust radiates in the far infrared. You basically have a large number of signatures, all of which give you this curve. So the confidence that we have in this curve is very high right now, because we have so many different signatures of the star formation rate, all of which give us this curve.
Okay, Nissim, the picture that you showed about the star formation, neutral hydrogen being very little, atomic hydrogen being very little. So what's the level, quantitatively, is that deficit that you see consistent with a drop in star formation of, it's not a huge drop by by 8 billion, right?
Yeah. So you can't do a straight conversion from mass to star formation rate density. But what you can do is that's what we've done in the paper that we're writing up right now. We've actually used this and the dependence of the H1 mass on the stellar mass to actually track the evolution of different galaxies. And to ask the question, so if I take a single galaxy, and I know how the star formation rate depends on the stellar mass, I know how the atomic hydrogen mass, because of what I said, I can actually tell you how the atomic hydrogen mass depends on the stellar mass. I can bin in stellar mass and tell you the dependence on the stellar mass. I know also how the molecular hydrogen mass depends on the stellar mass. So I know all of these things. Now I can actually evolve a galaxy in a Lagrangian manner such that I can track its evolution over this redshift range. So I can say that, okay, this galaxy starts with some stellar mass and some H1 mass and some H2 mass and some star formation rate. The star formation causes the H2 to be eaten up. And so you consume some amount of H2. You also have some amount of gas coming in. And I can ask the question, how much is the accretion rate? What is the change in the baryonic mass of this galaxy as a result of accretion compared to the star formation rate? So we've done that now for this redshift range, and it turns out that for that redshift range, the accretion rate does not match the star formation rate. It's about a factor of 4 or so less. So that's a pointed measurement. That's the paper that's coming out soon. When we do the same thing over here, it turns out in the nearby universe, about 3.5, 4 gigayears ago, it turns out that the accretion rates almost match the star formation rates. They almost bang on each other. But over here, there's a dramatic difference. Again, the same
so
factor.
There's something still unexplained in this.
It's kind of what I was saying, that the accretion rate is not enough to, the cause of the accretion rate being too low is, I think, the open question right now. So but the fact that the H1 mass is small is not open question anymore.
So going back to my question about the beam, if you showed that video where you had this, the orange galaxy.
Yes.
With the, so there, it's clear that, no, not this one, not the stacking, it's just your introductory.
Oh, you mean the older one? Yeah, okay.
Yeah, so there, what really strikes me is, that all the hydrogen moves to the center at some point, right? So if you have a big beam and that, and then everything is concentrated at this thing.
Yeah.
Is there a dilution that is happening because the beam is much bigger than where the hydrogen is?
No, not at all. So basically, what you're doing is that you're measuring the total energy coming from that region. So whether it's coming, it's not an average. It's simply the total amount. The signal you're getting is the luminosity. So you're simply measuring the number of photons coming from from the region observed by your beam. So whether that region is coming from here or it's just coming from a single point inside, there's no problem. It's an unresolved source, technically. Right. Yeah. So therefore, that's not an issue at all. You're not dividing by the beam.
That may be one reason you want the beam to be bigger?
Yes, yeah. Okay. So we want the beam to be big enough that it picks up all the gas.
Okay. Sorry, I'm sneaking another question in. So in that purple patch in your star formation region, which you didn't speak about, are you seeing it match with what the 9 billion years? I mean, I know that is preliminary, but maybe...
So I'll give you the short answer. The short answer is yes and no. What we did was that, so that's a super challenge. It's even more challenging than the region that we observed so far. So these observations, these observations you talked about are between 550 and 850 megahertz. These observations are between about 300 and 500 megahertz. The universe is not such a problem over there, but unfortunately all of you in the room are a problem. all of your TV signals and cell phones are not so bad over here, they actually hit you over here. But all the gadgetry that we have, including the silly pointer, is contributing to radio frequency interference. And we're living in this, with this background of RFI. And so we need to struggle against this background. That's really an issue. That's not the primary issue. That's one issue. But it's much worse at this frequency than at this frequency. The second thing that we have over here, unfortunately, is that it turns out that at that redshift, we only, as of today, have 1,000 galaxies in our beam with redshifts, with good enough redshifts. So which means that the sensitivity is not that good. There is a set of observations started early this year with the Subaru telescope, with the new spectrograph that they built, and that's another reason we chose that field, to actually get the redshifts of a large number of galaxies in exactly that region of the sky and exactly that redshift range. So again, in a couple of years, we'll have a ton of redshifts over there, we hope. But the thing that we're doing right now is that, what we did over there, because we didn't know, how bad the RFI environment, the interference environment was, we did a pilot study. So we did 200 hours of time, which is a large pilot by most metrics. And we just need to demonstrate that the noise actually goes down as expected. Because, given the background, we didn't know that. And it did. But we had estimated in the beginning that we need about 600 hours to actually see the signal. So right now, we don't see the signal. We see very tentative evidence of something over there, which I wouldn't trust as far as I can throw a large elephant. But it's consistent with the signal that we saw at this redshift. At about, it's about a 2 sigma signal. And so now we've been allocated another 325 hours to push this thing further. And we think that we might need another couple of 100 hours beyond that, but we have 325 more hours to go after this. And so we should, if that 2 sigma thing is real, we should see something at about 4 sigma with this thing in the next year or so. So we are kind of pushing away at it. We'll see how it goes. These are things where you're really, that is going to be super challenging. Because as I said, these observations were designed for stacking in the sense that the problem when you're doing a really deep observation of a single field, is that as you go deeper and deeper, systematic effects start to hit you. And the systematics are usually linked to that field. So now when you do stacking, you benefit by observing, by dividing your time amongst different fields, because then your systematics are different, and then they average out. They become like Gaussian noise, like one more source of Gaussian noise. The problem, so over here we had 7 fields, which is good news for us. Over here we have 1 field. So the question is whether the noise keeps beating down as we go deeper and deeper. And we are playing some tricks over there. Instead of pointing exactly here, we're kind of pointing here and then here and then here, and you're kind of jiggling it around a little bit. The hope is that we can, get some averaging from this. The answer is that we don't know as yet, but so far we found no reason to believe that we will not beat down the noise as we expected. But famous last words. So. It's all kinds. So for example, there's this truly nasty, in I think traditional fashion these days maybe I shouldn't say that. There's this terrible RFI between 360 and 380 megahertz, a 20 megahertz wide patch, which is coming from the Muir satellites. You simply cannot work in that frequency range. It's just not possible. So that 20 megahertz is gone, it's dead. So we are actually right now, the thing that we are doing over there is between 380 megahertz and 500. We've not even started bringing in the stuff below 360, where there's much more RFI. Between 380 and 500, there's a patch of RFI above 480 megahertz, which comes from digital TV. So digital TV is unfortunately coming into India, and we still at the GMO, and it's not there in most of India, but we are seeing digital TV stations from Aurangabad right now. Luckily, they switch off at night. So they switch off about 11 o'clock at night, so we're trying to observe only at night. Now, of course, this is difficult because we're targeting one field, and so we can only observe some times of the year and so on. So all these complications come in. So digital TV is an issue. If we throw away that part of the band and live only with 380 to 480, then it's only narrowband stuff. It's just small spikes, which you then go and whack them on the head and filter them out.
Okay, with that, let's thank Nissim once again. I invite Tarun to present a souvenir to a speaker.
Oh gosh. Thank you. Nice.
Yeah, thanks everyone, and we have high tea downstairs.
Sure. Yeah. Hang on. Sorry?
Just come to
Yeah, we'll have to go and grab some dinner. I've been for a long time, so.